Okay, in this exercise we want to solve this ODE using the method in section 2.3. Now, the method in section 2.3 requires you to remember this expression, e integral of px dx. Okay, so what in the world is px? Well, before you solve the ODE, we need to rewrite the ODE without anything here multiplying the derivative. So if we divide both sides by cosine, so we need to get rid of the cosine here. We get dy dx plus sine over cosine equals to 1 over cosine. Okay, so this is p of x. So this expression will be our integrating or integration factor. Okay, so just a quick review here. So what in the world is this integration factor? What does that do to the ODE? Well, if we multiply the ODE, both sides of the ODE by this factor here, then the left-hand side becomes the derivative of a product, so which is easy to integrate. So in other words, if we have multiply both sides by that factor, dy dx, and then p of x, right? P of x it's here with the y. And then of course this will show up on the other side as well. But if you look at this side, then this can be written as a derivative of a product, which is e integral p of x dx times y. And that's easy to integrate because right, we integrate with respect to x, then the derivative disappears, right? So that's the idea. So let's figure out what this is. Integral of sine over cosine, that's tangent, right? And now integral of tangent, if you look at the integration table at the beginning of the book on the cover, I'll provide the integration formulas for you on the test. But an integration of tangent is actually negative of natural log of cosine. So this is negative of natural log of cosine of x. And then plus c, we don't need the plus c there. In the derivation of this method, the c goes away. We don't need that. So we don't need to put the c here. Only at the end, when you solve the ODE, then you can put the plus c at the end. Now, e and natural log, they cancel each other, but we have this negative sign. We need to get rid of that first before we cancel it. So we can write that as 1 over e natural log of cosine of x. And then e natural log, they cancel. This is 1 over cosine of x. Now, you can see the restriction that we have here. We don't want cosine to be 0. We don't want zeros in the denominator. So cosine will be 0 when x is pi over 2 or negative pi over 2. So we're going to pick that interval. Okay, so this is good on the interval negative pi over 2 to pi over 2. So that's the interval that we're going to use for our ODE. All right. So now this is integration factor. So what do we do with it? We multiply both sides of the ODE. So it would be 1 over cosine x, right? Both sides, dy dx plus, let me put tangent here. Okay. So back to the ODE. So multiply, see here's the ODE, multiply both sides by that integration factor. And so this becomes 1 over cosine in dy dx plus 1 over cosine tangent x. And then on this side, 1 over cosine squared. I don't have to, manipulate that expression because I know that becomes derivative of the integration factor times y. So I can simply write this as derivative integration factor times y. Okay, and if you want to check that, that's fine. So if you look here, right, derivative of this product is the first expression times derivative of the second plus the first derivative of the first, which is that, right, times the second function. Okay, now we can integrate. So let me move this over here a little bit. So I put integrate both sides. And right, integral of derivative, so they cancel, so this becomes 1 over cosine x times y. And then this integral here, 1 over cosine squared, that's actually secant squared. And integral of secant is also a standard integral. Integral of secant squared is tangent. So this is 1 over cosine x equals to tangent. Now we put plus c. Let's solve for y. This is cosine x, tangent x, c times cosine x. And since tangent is sine over cosine, the cosine will cancel. So what is left here is just sine. So that becomes the solution. And this is on the interval negative pi over 2 to pi over 2. Right, and that interval, it comes from this fact here, that we don't want cosine to be negative. So we want to choose an interval where cosine is nice, right? No, it's not 0, so we don't create problems with the denominator there. So that's the solution.